Hey, this is Tanmay Shukla. This is Lab 3 for Physics 2211 at Georgia Tech. So, part 1 of Lab 3, you find the mass of a black hole. So, introduction for part 1 is to determine the mass. Objective is to determine the mass of an unknown black hole by analyzing the orbit of a star around it. Given data, the star's mass is 2 times 10 to the 30 kgs. The black hole is located at the origin, and in unique position data is generated at the beginning using the starter code tied to a specific Georgia Tech email. Method for this lab was to assume gravitational force on the black hole is the only force on the star. We use 1 day as a time step between data points, and we calculate the net force on the star and use it to estimate the black hole's mass. At the end, we report a single mass value by averaging individual readings of the mass that we get. So fundamental physics principle that we're using in both part 1 and 2 of this lab, where we have Newton's laws of gravitation first, we have Newton's second law, we have the velocity update formula, we have the position update formula, and we have the parallel and perpendicular components of a force. We know the parallel component can only change the magnitude of the speed, and perpendicular component can only change the direction of velocity. So this is the initial conditions. Um, this is the calculation loop. We iterate and we find dp over dt, use that to find f net, and then we equate that to Newton's law of gravitation, and we find the mass of the black hole. And our final black hole mass estimate after averaging all values that we got was 1.894 times 10 to the 34 kgs. That's just massive. For part 2, we simulate a ship, planet, and a moon. Our scenarios: if we have a planet, a moon, and a spaceship. The planet stationary at the origin, and the moon orbiting the planet create a two-body system. So our spaceship starts on the moon and must orbit both the planet and moon in a figure-8 path without crashing. So goal is to determine an initial velocity for the spaceship that allows it to circle both bodies, experiencing gravitational pulls from each, while being in a figure-8 orbit and not crashing. So this is the initial conditions of our glow script model. We find the mass of the planet. We initialize the ship speed, and x is 20,000 and ship speed y is 14,250, and we just found that using trial and error. Um, this is the calculation loop. We find the fnet on moon. We find the fnet on ship. We have used that to update the position of the position and velocity of the moon and the ship, and we simulate from 0 to 700 hours. And this is the output we get, and you can see that it somewhat forms a figure-8 body. So that shows it's successful and it didn't even crash. So discussion question 1: what does it mean? So the net force, total gravitational pull acting on the star, and the rate of change of momentum is how the star's momentum changes over time, essentially ma. So we know that if once again the rate of change of momentum, we can equate that to net force, but we also know that the parallel component can only affect the star's speed, and the perpendicular component can only affect the star's direction. That is the direction of velocity, curving the orbit essentially. And so the key idea here is the net force causes change in momentum, and they should match for if all forces are accounted for. What if this imagined system has a black hole, a star, planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Think about all the interaction in the system. Would there be any dominant interactions, or would they all contribute more or less equally? So if you wanted to model the entire system, black hole, star, planet, moon, and spaceship, you need to account for every gravitational attraction between all pairs of objects. In practice, the black hole's pull on a star is usually dominant at large distances, but each smaller body, the planet, the moon, and possibly even the spaceship, can still affect each other if they're close enough or if you need high accuracy over longer times. You'd also have to track each object's changing momentum step by step, updating positions and velocities based on the sum of all relevant forces. So you have to account for all the forces acting on the object, essentially. Some of the possible sources of error we could have. So one is numerical approximation. We break the motion to small time steps, but they're still discrete time steps. They're not continuous. It's not really calculus. So error could creep in, or especially accrued over time. Then there's uncertain measurement and initial conditions. Maybe our star's starting position and velocity wasn't exact, and these small errors can grow over time, changing the orbit noticeably. Computer precision, computers store numbers only up to a certain number of digits after the decimal. So this could even introduce, again, error over time. Thank you, that's it. This is Tanmay Shukla signing off for Lab 3 at Georgia Tech. Thank you.